Welcome to our video lectures on confidence intervals. In this first video, we're going to talk about some basic issues about confidence intervals, such as the motivation. Why would we want to use confidence intervals in the first place? And then talk a little bit about the purpose that confidence intervals serve. So to start off, why do we need confidence intervals? We've been talking about statistical inference. That is how we say something about a population from a sample. And we've already covered one type of statistical inference, which is hypothesis tests. So we saw how taking a sample and running a hypothesis test tells us something about our guess regarding some population parameter. The problem with hypothesis tests is they don't tell us everything. And I want to show you a few things that people very often want to be able to obtain from data that you can't get from a hypothesis test. So we know that a hypothesis test can be used if we want to see if some sort of change in a population parameter has occurred. And we know from the central limit theorem, if nothing happened, what the estimates would look like. I'm showing here kind of like a scatter plot of the sample percentages we would get in an example that we considered a couple modules back. So we were looking at a hypothesis test to see if the percentage of motorcyclists injured in accidents had changed after the helmet law had been repealed. And if there was no change, if the percentage of motorcyclists that were injured was still 80%, we would see this sort of scatter. And the central limit theorem actually tells us exactly what this scatter looks like. It's a normal distribution. And of course, the way we test that hypothesis, right, is we go ahead, we take a sample, we compute the sample percentage, our estimate, and we ask, how likely is it to come from this distribution that we'd get for the sample percentages if the null hypothesis was true? And so if a change occurs, we're going to see something like this. Our sample percentage is not going to look like part of the random scatter. It's going to be a couple standard deviations away. So it would be unusual to get if the null hypothesis was true. And so this tells us now that pi, the population percentage, or in this case, the population mean of the sample percentages, is no longer the old value. It's no longer 80%. It's centered around some new value of pi. Okay, so this observed sample percentage is really part of the random scatter around some new population parameter. But notice there's a problem here. What is the new population percentage? We'd like to know. And that's something that we don't get from a hypothesis test. Also, sometimes we don't need a hypothesis test. So sometimes, for example, we just want to estimate a parameter, maybe the population percentage, okay? We're not testing to see if some sort of change occurred. And so as an example, if we wanted to determine what percentage of voters would, say, re-elect Trump, we just want to estimate the population percentage. Okay, we're not running a hypothesis test. We just want an estimate. Sometimes also, we can't even form a hypothesis about the population parameter. So notice, for example, the hypothesis is an educated guess. But sometimes you might not have any background. You don't even know what pi is. And a really good example is the error barometer discussion exercise we did. For most students, their hypotheses turned out not to be good. When they took their sample data and they asked, how likely am I to get this sample percentage if my guess was correct? For most people, it turned out it was very unlikely. It was several standard deviations away. So when we don't even have an idea as to what the population parameter is, be it the population mean or population proportion, it doesn't make really any sense to test to see if some sort of change occurred. One big thing that hypothesis tests leave out is they don't tell us how precise our estimators are. So we keep coming back to this really main theme in the course: samples estimate populations. And one thing we know is that our estimate is almost never equal to the true population parameter. And here I just use percentage as an example. And even if it was, we wouldn't know because we don't know what the population parameter is. We also know from the central limit theorem that larger samples should give more precise estimates. Okay? And let me change that. That should be sample estimates, but I'll just write estimates. And so there's some real questions here that we have about this notion of precision. Precision is how close the estimate is to the parameter. First of all, how do we quantify precision? And this is difficult because the estimates can be all over the place. Okay? You can have estimates really close. You can have estimates far away. So how are we going to quantify what we mean by precision? And the second thing we want to understand is we want to have a quantitative understanding of how sample size affects our precision. So, for example, you could have two people both taking a survey. One person uses a sample size of 100. Another person uses a sample size of 2,500. We intuitively think the person with the larger sample size is going to have the better estimate. But there's two issues. First of all, the person who took the small sample size could get lucky. Their sample estimate might line right on the population parameter value. So we know that it's not always true that a larger sample for one sample is always better than a smaller sample for another sample. So we have to kind of reconcile this fact in our mind. We have on our minds this notion that on average, larger sample sizes give more precise estimates. But we have to kind of give a better definition, okay, because it doesn't work for individual samples. So we need to define what that means. But the other issue here is how much better is the estimate from the larger sample size? See, here's the thing. Good data is expensive to collect. So if you're going to collect 25 times more data, you better know, okay, how much better your estimate's going to be. And how do you know when to stop? Maybe 2,500 is not enough. Maybe to get an estimate as precise as you want it, you should have taken 10,000 people. So we need some sort of quantitative understanding of how sample size is going to affect our precision. We want a formula, in other words. So the answer, first of all, to how we define precision is we put an error bar around our estimate. We say, okay, we know our estimate is most likely not the actual population parameter value. There's some error in it. So we're going to put some sort of error bar around our estimate. And we're going to call that error bar the margin of error. And I'm sure that many of you have heard that term. And it's going to turn out that the margin of error is dependent upon something called the confidence level. So notice that we're working with confidence intervals. We're going to have a really good understanding of what confidence means in this class. And we're going to discuss that in a lot more detail and very thoroughly next week. Also, the central limit theorem lets us answer this second question. It turns out that we can actually get from the central limit theorem a formula for the margin of error. And we're going to see that that formula involves the size of the sample, how much variability our variable has, and this thing called the confidence level. We're going to see that all three of these things affect the precision. So now I want to give you a reading quiz here. So your first question will be related to the air barometer discussion problem. And it's asking if you think it would have been worthwhile for that discussion to have run a hypothesis test on your guess for the population percentage. So for your country and for your question, you made a guess as to what pi is. In hindsight, okay, do you think it would have been a good idea to have run a hypothesis test? So take a minute and think about that and choose the response that you think best answers the question. Okay. So now we're going to get into the anatomy of the confidence interval. What purpose does it serve, and how is it kind of set up? How is it constructed in general? To understand the purpose of a confidence interval, you have to understand that in statistics, we actually have two types of estimates that we can compute. One is called a point estimate, and the other is called an interval estimate. And the point estimate is the single value that best estimates the parameter's value. And so we know from before what that is. It's generally the sample estimate, right? Samples estimate populations. That's the idea. And so for a quantitative variable, the sample mean, x bar, is the single value, i.e. the point estimate, for the population mean, mu. And we know that for a categorical variable, the sample percentage, p, is going to be our best single value, or our point estimate, for pi, the population percentage. Now I'll give you a quick heads up here. The book sometimes uses this p with a circumflex over it to represent the sample percentage. That's pronounced p hat, by the way. I'm not going to use that, but you'll see that in the book. Now, a confidence interval, however, is what we call an interval estimate. And what it is rather than estimating the parameter by a single point, we're going to give an interval of values, just like an interval on a number line. And this interval of values is where we're going to think the actual value of the parameter is. And usually, interval estimates in statistics are confidence intervals. So if you hear that the confidence interval for the percentage of voters who will support Trump is the interval 44% to 48%, what that means is we think the true value for the population proportion is between 44 and 48%. And the text sometimes writes this interval as an inequality. And from high school math, we all know that these two things are equivalent ways of writing a range of values, right? Now, if we look at how we actually construct a confidence interval, it looks something like this. And the interval here, which is in red, is the range of numbers that we are confident the value of our parameter is in. It is always centered around the sample estimate. So if we're working with a population proportion, it's going to be centered at p hat or p. If we're working with a population mean, it'll be centered at x bar. Now, this isn't true for all confidence intervals. I should just make a quick little caveat here. However, for the confidence intervals that we're going to work with, it is going to be true. And these endpoints are called the lower limit or the lower endpoint of the confidence interval and the upper limit or upper endpoint of the confidence interval, respectively. And this half width or this error bar that we put around our estimate is called the margin of error. And the book uses a notation, capital E, for margin of error. So you should note that. Now, there are some nice relationships between the estimate, the endpoint, and the margin of error that we want to make sure we understand. So here is our confidence interval. And we want to work out some relationships between the endpoints and the estimate. So first of all, to get the lower limit or the lower endpoint, we subtract the margin of error from the estimate. And from the upper limit or the upper endpoint, we add the margin of error to the estimate. Now, if we wanted to go back and solve for the sample estimate or the margin of error, if we were given the confidence interval, we can do that too. We notice that the estimate is the midpoint of the interval. In other words, it's the average of the upper and lower limit values. And we can see that right from these two equations on the left-hand side. If we added them, we would get lower plus upper limit on the left-hand side. The margin of error would cancel out, and we would get twice the estimate. And we could algebraically solve for the point estimate by dividing by 2. Now, if we look at the margin of error, we realize it's the interval half width, right? It's half the interval width. So that means that you could subtract the upper limit from the lower limit and divide by 2. And let me go ahead and change that to a negative. Okay. So that's one way of getting it, right? If I subtracted the upper limit from the lower limit, I would get the width of the interval, and the margin of error is half of that. Or we notice that if we subtract the estimate from either endpoint, since the estimate is the same distance away from either endpoint, which is the margin of error, and take the absolute value, we can get the margin of error that way also. Okay, so let's have some fun and try to apply these facts to a reading question here, reading quiz question. So using data selected from a survey of 1,200 adult women, it is reported that the confidence interval for their height is the open interval 62 inches to 70 inches. And so from this given confidence interval, we want to answer the following two questions. What was the average height for the women in this sample? And what is the margin of error for this confidence interval? So go ahead and you want to just pause the video when the question comes on and answer this reading quiz question. Okay, that is all for this first video. In the second video, it will be a lot more involved and complicated. We'll start to talk about how we actually get confidence intervals, how we use StatCrunch to compute them and things of that nature. So it'll be definitely more long and involved, and it's one that you want to pay attention to. All right, thank you.